Yes, Dada.
Okay, so we will discuss the limits of polynomial. Only one topic we'll discuss because this one is a bit difficult. So mainly when you do limits of any function, you need calculus, but in this one I will provide you all the proofs without using any calculus. But it will be a little bit difficult to follow. So you might want to skip it right now, but at least remember the results, even if you don't remember the proof. So suppose we have a non-constant polynomial. Then this polynomial cannot have both an upper bound and a lower bound. By upper bound, I mean a real number m such that p of x is always lesser than or equal to m. And by lower bound, I mean another real number, say n, such that p of x is always greater than or equal to n. So a non-constant polynomial will not fall into either of these cases. So how do we prove that? Suppose we have the polynomial p of x equal to an x power n plus an minus 1 x power n minus 1 dot 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 up to n. It is a polynomial of degree n which is greater than or equal to 1 because we want a non-constant polynomial. So there are few cases to deal with. We will deal with the case where the leading coefficient is positive. The negative leading coefficient case is similar, just you have to consider minus of p of x to do that. So the first step is to choose a real number b which is smaller than all of ai by an for 0 lesser than equal to I lesser than equal to n minus 1.
Dada,
You
why?
can Okay, so we are trying to prove this that a non-constant polynomial cannot have both an upper bound and a lower bound. So in proving this, the first step is something like this. Now, why I am doing this, that you will see very soon in the next slide itself. Now, the question is, do you understand that why choosing such a real number is always possible? Like you have n real numbers here, a naught by an, a1 by an, and so on up to n minus 1 by n. So, are all of you sure that it is possible to choose a real number b which is smaller than all of them?
Yes, Dada.
Right. So, basically, there are finitely many real numbers. So you can always choose their minimum and choose a number which is smaller than that. That's why it is possible to choose a real number which is smaller than all of them. Now observe that whenever x is greater than 1, we get a certain inequality. So what do we get? So from the expression for p of x, let us factor out an. Then we will get this expression. An times within brackets x power n plus summation I equal to 0 to n summation I equal to 0 to n minus 1 ai by an x power I. It should be n minus 1 here, sir. So b is smaller than all of these numbers. So ai by an is always lower bounded by b. And then you are multiplying x power I both sides, and that is possible because x is greater than 1, so it is greater than 0 also. So you are multiplying positive number both sides, that's why the inequality is not changed. And then you are adding x power n both sides and then again multiplying an both sides. Again an is assumed to be positive, that's why the sign of inequality does not change.
Dada, I understood till that part, that polynomial expansion, and then we replace that ai by an in the inequality by b means it will always be greater than this. Then after that step, the last line I could not understand how it came.
Okay, I'm going to that. So did you understand this part, that how p of x is lower bounded by this expression an times x power n plus b times summation I equal to 0 to n minus 1 x power I? Did you get till here this?
Yes, Dada.
Okay. After this, you have to apply GP series. I'm sure you will have a class on this later on. But do all of you have an idea of what GP series is?
Yes, Dada.
Yes.
Okay, so this thing, this summation I equal to 0 to n minus 1 x power I, this is a geometric progression. So you can sum it up for x not equal to 1, and for x equal to 1 is also possible, but this formula won't work in that case. If x is equal to 1, this summation is simply n. But if x is not equal to 1, the summation is x power n minus 1 by x minus 1. So do all of you get how we arrived at this expression?
Yes, Dada.
So basically, p of x is then lower bounded by an times x power n plus b times x power n minus 1 by x minus 1. So that's all we need to know now. You would better write this down in a piece of paper or a copy or something like that. We will need this expression later on.
So we have got the lower bound, right?
No, I am not. I have not yet proved anything right now. Right. I want to prove that px has neither an upper bound nor a lower bound, but right now I have not proved anything. I am just doing a step. Now, why I am doing it, you will see it just. Basically, I am trying to prove that it does not have an upper bound. So I'll show you why I did this. So I'll turn over to the next page. So you might want to write down the expression because you might need it later. So let's go to the next page. So first, I want to prove that this p is not lower bounded by any real number. So remember that initially we assumed that the leading coefficient of p is positive. So what I'm trying to show is, if the leading coefficient is positive, then p is not lower bounded. So basically, initially we wanted to do either of two things, either prove that p does not have a lower bound or does not have an upper bound. For positive leading coefficient, we will prove that p does not have a lower bound. So how do we show that? Consider a positive real number m. We want to show that there is some x for which p of x is greater than or equal to m. So we want to show that p of x will eventually exceed m somehow. Now this is equivalent to proving that p is not lower bounded by any real, because if it is not lower bounded by a positive real number, it cannot be lower bounded by any real number. Correct? Do all of you get this part of the argument?
Can you repeat once more, Dada?
Okay, so I'm trying to prove that when the leading coefficient of p is positive, p is not lower bounded by any real number. So instead, I will show that p is not lower bounded by any positive real number. So do you see why these two statements are equivalent? That p is not lower bounded by any real number is equivalent to saying that p is not lower bounded by any positive real number.
What if it is lower bounded by a negative real number?
Okay, so think about it. If, okay, I will show you the steps one by one. I'm writing it in the chat. See, p is not lower bounded by any real number, then p is not lower bounded by any positive real number. So one statement implies the other. Now to show equivalence, we have to show the other way around also. That is, if p is not lower bounded by any positive real number, then we want to show that p is not lower bounded by any negative real number or not lower bounded by zero also. So how do we do that? Say we choose the positive real number, say m equal to 1. That means there is an x such that p of x is greater than or equal to 1. But then 1 is greater than 0 and 1 is greater than any negative real number. then for this x, p of x is greater than 0 and p of x is also greater than any negative real number. So now do you see why not being lower bounded by positive real numbers is same as not being lower bounded by any real number? If you don't get it, write it in the chat, okay? So you should reply. I mean, better reply in the chat. Otherwise, you can unmute yourself if writing is difficult. But unless you reply, I won't know if you understand or not. You could take m as half also. Anything positive could have been taken. Half, 0.05, anything. I just wanted to show that not being lower bounded by any. No, we have to prove that if it is not lower bounded by any positive real number, then it is not lower bounded by 0 and not a negative real number also. So what do we have to show? That p of x can exceed 0 and can also exceed any negative real number. What we know already is p can exceed any positive real number. And every positive real number exceeds 0 and any negative real number also. That's why p exceeds every negative real number and 0. I mean, we have to show that p of x is greater than equal to say minus 1. And what we already know is p of x is already p of x can exceed any positive real number. So let me choose the positive real number to be 1. P of x can be made greater than equal to 1 for some x, not for all x, for some x. But then 1 is again greater than minus 1. So that proves that for this x, p of x is greater than equal to minus 1. Now do you understand what we are trying to do? We have information on positive real numbers. P of x becomes larger than any positive real number. So automatically it becomes larger than any negative real number. It becomes larger than 0 also, because every positive real number is larger than 0 and negative real numbers. So do you get the argument now? Okay, so everyone else should reply also. Only 2 or 3 people replying is okay. So instead of focusing on all kinds of real numbers, we will focus only on positive real numbers now because it's equivalent. We want to show that there is some x for which p of x is greater than or equal to m. Now, it turns out that while you try to prove this, you generally end up proving a much stronger statement. And the statement is, there is a y such that p of x is greater than equal to m for x greater than or equal to y. So what is this statement saying? It says that not only does p exceed m, indeed, there is some value of x after which p exceeds m. That is, for example, if I take the polynomial p of x equal to x square. Now I know that there is some x for which x square is greater than or equal to 1, let us say. There is some x. But I know something even stronger. That is, for all x greater than or equal to 1, x square is greater than or equal to 1. Let's say if I want to prove that x square is say greater than or equal to 3 for some x. But I know something even stronger. For x greater than or equal to square root of 3, x square is greater than or equal to 3. This statement is stronger because it says that after some point, all of the values will exceed m, not just one value, but all. And indeed, it turns out that proving this statement is much more intuitive than proving the first statement. That is, for some value, it exceeds m. This one is a bit weird statement. Like, why should just for some values it should exceed m? For all values, it should exceed, or at least for an interval, it should exceed. So the statement is saying that after some point, after some value x equal to y, all the values will exceed it. So do you understand the statement? Okay. So, so when you do real analysis in later studies, or even if you just learn calculus, not up to real analysis, you will often come across the term large enough. Now, what does this large enough mean? Large enough means after some value of y, some statement holds. That is exactly this kind of a statement. There is a y such that p of x is greater than equal to m for x greater than equal to y. Often you will find it rephrased in many books as for large enough x, p of x is greater than or equal to m. So this statement means nothing but there is a y such that for x greater than equal to y, p of x is greater than equal to m. That's why we use large enough. Okay. So now observe that there is a lot of freedom in choosing y. Like for example, in the example I gave you earlier, this x square greater than equal to 3, the exact point at which x square x is 3 is y equal to say, or let's say x equal to square root 3. I mean, if you observe the graph of x square, then the exact abscissa of the point at which it exceeds 3 is square root of 3. Yes, on the negative side there is another one, but we are considering only the positive side, right? But that doesn't mean that I have to choose y equal to square root of 3 only. I could have chosen, say, y equal to 2. Because even for y equal to 2, this statement holds. Because if x is greater than equal to 2, then x is greater than x square is greater than equal to 4, which is again greater than equal to 3. So if I ended up proving that for x greater than equal to 2, x square is greater than equal to 4, then also we are done. We had to choose some y, not necessarily the optimal y. Some y such that for x greater than equal to that y, x square is greater than equal to 3. Very well, let us choose x equal to 2 because maybe we don't like dealing with square roots and all. So when x is greater than equal to 2, x square is greater than equal to 4, which is greater than equal to 3. So okay, we proved it for y equal to 2 now. Doesn't matter, we needed some y. Could have been some 2 billion, 3 billion, anything. Okay, so do you all get like why did I relax this statement a little bit? Because we don't like dealing with complicated expressions like square roots and all. Okay, so first only let us assume that x is greater than. This confirms with our discussion right now because we said that we don't need the optimal y. Any y will work, just we need some y. So first only let us consider the statement that y is something greater than 1 and we will consider all values of x greater than 1. Then in the previous slide, we saw that p of x is lower bounded by this quantity, this an times x power n plus b times x power n minus 1 by x minus 1. So if I am trying to show that p of x is greater than equal to m for sufficiently large x, does it not suffice to prove that this quantity, this an times x power n plus b times x power n minus 1 by x minus 1 is greater than or equal to m? So, do you all think that this statement is sufficient? Is if we prove this inequality, then the original inequality holds?
Yes, Dada.
Okay, so we will prove this one and realize that this thing is a lot easier to prove because in that one we had something like a naught plus a1x plus a2x square and so many ai's there. But here we have to deal with only an an and there is a b somehow. So only these two real numbers, if we don't know, we know that an is positive, but that is all we know. But still there's a relaxation and it's much easier to prove. So what is our aim here? We are trying to show that this quantity exceeds m for some value of x, and not only that, for large enough x, that is for some x greater than equal to y. So now again we don't like fractions, so let us multiply by x minus 1 both sides And these two statements are equivalent because when you multiply x minus 1 both sides, we are multiplying a positive real number because x is greater than 1 already. So if you multiply out and divide by an, what you get is, we want to prove x bar n plus 1 minus x bar n plus b times x bar n minus 1 is greater than or equal to m by n times x minus 1. We want to prove this for large enough x. And this quantity is again much easier to deal with. There is no fraction. Everything is in terms of only two unknown real numbers, b and an, and this m is given. And then we have much simpler quantities, like we have only x bar n plus 1 and x bar n, and on the right hand side we have an x. So we don't have anything like x, x square, x cube, x bar 5, etc. So only two or three powers we have to deal with. So note down this expression now, because I'm going to turn over the page and this expression is going to be useful later. Only the last expression will suffice for now.
But how do we prove that last expression is true?
Yeah, I'm going to prove that in the next
Dada,
slide.
is it x to the power n minus 1?
Which
N
part?
plus
Dada, that one, b into x to the power n minus 1.
X bar n minus 1. Minus 1 is separate, not x
Okay.
power n minus 1. Okay. Just multiply out this thing. This x bar n minus 1. This one has come from here. Okay. So that's how it is. So again, to confirm that we are all on the same page, I'm not trying to prove this for all x. It might not be true for all x. So what we will prove is that after some value of x, this is true. So let's go to the next slide and see how we can prove this. Okay, so now we do another relaxation. Consider x greater than equal to 2. So initially we were focusing on greater than 1. Now let us focus on greater than equal to 2. So see that we are doing a lot of relaxations here. And the reason why I'm doing this is simple. It will make our calculations easier. And are we allowed to do that? It is very much allowed because there is a lot of freedom in choosing y. Okay, so when x is greater than equal to 2, we have x bar n plus 1 minus x bar n is greater than or equal to x bar n plus 1 by 2. So I hope all of you can understand how this is derived. Just transfer x bar n plus 1 to the other side, x bar n to this side, and then just remove the x bar n, and then you will see that this is equivalent to saying x greater than equal to 2. So everyone got it, that how we arrived at this inequality? That y for x greater than equal to 2, this inequality must hold.
yes, Dada.
Okay, so since everyone doesn't agree all the time, you should better write it in the chat. Don't reply on the mic. So I'll explain again. Basically, first we have to know that we can do a lot of relaxation. We are free to choose any large value of y, 2 billion, 3 billion, any number of billions, anything. So we are focusing on the interval 2 comma infinity, close 2 comma infinity. Initially we are focusing on open 1 comma infinity. Now we are focusing on close 2 comma infinity, that is x greater than equal to 2. So when x is greater than equal to 2, then if you just manipulate this expression a bit, do you not get that x bar n plus 1 minus this x bar n is greater than equal to x bar n plus 1 by 2? Okay, this one should be, oh sorry, this should not be x square, it should be x bar n. So it's simple, just transfer x bar n plus 1 by 2 this side and x bar n that side. Okay, there was one student who asked this, so if you reply then I will continue. Okay. So there is another question here, that is, should it not hold for x greater than equal to 1 as well? Okay, so does it hold for x greater than equal to 1? If x equal to 1 only, it does not hold, I think. Because for x equal to 1, left hand side is 0, right hand side is half. So, okay, even if it did hold for some expression, it doesn't matter. I told you that it is very much possible to choose any large value of x. As I said earlier, we don't need the optimal value of y. Any y will work. Like in the x square case, x square exceeds 3 for x greater than equal to root 3. But we can choose anything larger than root 3 also. So if x is greater than equal to 2, 2 is already greater than equal to root 3. So x square is greater than equal to 3 for x greater than equal to 2 also. So it is very much possible to choose any large value of y larger than the optimal value. So even if for x greater than equal to 1 it would have hold, then even then it's not much of a problem. Suffices to prove for x greater than equal to 2. So now, why did I do this? Why did I lower bound this x power n plus 1 minus x power n by x power n plus 1 by 2? Because observe that, then again, it becomes much easier to deal with these expressions. If you go back to the previous slide, here we were dealing with this expression x power n plus 1 minus x power n. We were trying to lower bound this whole expression, and it's a little bit difficult to deal with two powers together. So we are trying to reduce it to one power. We are lower bounding x power n plus 1 by minus x power n by x power n by 2 for sufficiently large x. So now, in order to prove this inequality, it suffices to prove the other inequality. That is, it suffices to prove that x power n plus 1 by 2 plus b times x power n minus 1 is lower bounded by m by n times x minus 1 for sufficiently large x. So does everyone understand this step, that why it is alright if we prove this inequality instead? Okay, so more people should reply, as I always say. Okay, nice. So now again we are on to prove this. So again now we have two powers, x power n plus 1 and x power n on the left hand side. Again, this is a little bit annoying. We don't like dealing with two powers. So we will deal with one power right now. And that's why we will prove another relaxation. That is, we will prove that x power n plus 1 by 2 plus b times x power n minus 1 is greater than or equal to x power n plus 1 by 3 for large enough x. Now, if we can prove that, then we will have only one power to deal with. So how do we prove that? That for large x, this inequality is true. Let's go to the next page and see how we prove that. Now, this proof is a little bit complicated. Okay. Initially, we had chosen x larger than 2 in order to arrive at that inequality, the last inequality. That is with the greater than equal to m by n times x power n m by n times x minus 1 on the right hand side.
Dada,
While
can you
proving,
go to the last slide once?
okay, so last slide. So we are trying to prove this inequality, and for proving this, we will prove an intermediate inequality. This one, that x power n plus 1 by 2 plus b times x power n minus 1 is lower bounded by x power n plus 1 by 3. If we can prove that, then after that we have to prove only that x power n plus 1 by 3 is lower bounded by m by n times x minus 1. And so we will just use the transitivity, that if a is greater than equal to b and b is greater than equal to c, then a is greater than equal to c. So we will prove this last inequality now, this with the x power n plus 1 by 3 on the right hand side. And this proof is a bit complicated, and if you are done, let me know. I will move on to the next slide. Okay, so
Yes, Dada. You can go ahead.
initially we had taken x greater than 1 and x greater than equal to 2. Those are the two relaxations we had made earlier. Now we make another okay, meeting ending in 5 minutes, so rejoin the meeting. Vanit, end the meeting just now. We will rejoin.
Dada, what's that? X larger than both 2 and 6 mod b minus 6p?
Okay, we have only 5 minutes left, so let's rejoin. So when everyone is here, let me know. Okay, so initially what we were doing is we had considered x larger than 1 and 2. So now in order to prove the previous inequality, let us make another relaxation. So consider x larger than both 2 and 6 mod b minus 6b. So b is that real number which we had chosen earlier, smaller than all the ai by ans. And 6 mod b minus 6b, all of you know what mod means. Mod, absolute value. That is, if b is positive or 0, then mod b is equal to b. If b is negative, then mod b is equal to minus. So x larger than both 2 and 6 mod b minus 6b. Why we chose this peculiar number, that we will see very soon. This also implies that x greater than 0. Okay, it should be implies, not imply. Okay, I missed the s. So then we have x greater than equal to 2 greater than equal to 1. But if x is greater than equal to 1, x power n is also greater than equal to 1. So now, if x power n is greater than equal to 1, then we will see very soon what we have. But let's make use of this inequality once, that is x greater than equal to 6 mod b minus 6. So by transferring 6b to the left hand side, we get that x plus 6b is greater than equal to 6 mod b. Now we have two inequalities, and that too with all terms positive. That is x power n greater than equal to 1 and x plus 6b greater than equal to 6 mod b. So since all terms are non-negative, we can multiply and keep the sign of inequality preserved. So what do we get? We get that x power n times x plus 6b is greater than equal to 6 mod b, which is again greater than equal to 6b. Now multiply x power n on the left hand side with x and 6b and transfer 6b to the left hand side and just manipulate the inequality a bit, and you will get this inequality. X power n plus 1 plus 6b x power n minus 6b is greater than or equal to 0. Now the remaining part is just manipulation. Divide by 6, take b common, you will get x power n plus 1 by 6 plus b times x power n minus 1 greater than equal to 0, and write 1 by 6 as half minus 1/3, then you will get x power n plus 1 by 2 plus b times x power n minus 1 is lower bounded by x power n plus 1 by 3. And
Dada,
this
I
is what
could
we
not
have.
understand how from the second last step it got to the last step, that x is n plus 1 by 2.
Okay, so what is half minus 1/3?
1 by 6.
Okay, so write 1 by 6 as that.
Okay, Dada, got it.
Okay, so basically that's what we had to prove. So what we concluded is for x which is larger than 2 as well as 6 mod b minus 6b, this inequality holds. So now questions might arise that from where did you get this 6 mod b minus 6b? How did you arrive at this? It is nothing but backtracking. I knew I had to prove x power n plus 1 by 2 plus b times x power n minus 1. This is lower bounded by some nice expression, and I know, let's say from experience or let's say from calculus, to be honest, that is going to be larger than x power n plus 1 by say a for any a greater than 2, and that's why I chose a to be 3, and x power n plus 1 by 3 is what I chose. That's why I wanted to prove this inequality. This x power n plus 1 by 2 plus b times x power n minus 1 is lower bounded by x power n plus 1 by 3. And after that, I just did backtracking. That what can I do to prove this?
But
Transfer
Dada, how can we prove that x will be larger than 6 mod b minus 6b?
No, I am not true. I am not telling that for all x this is true or anything like that. I said earlier that I have to choose a y such that for x greater than equal to y, the inequalities which we are trying to prove hold. Now, y you can choose to be anything as large as you want. We only need a y such that after that value of x, that is after x equal to y, p of x will exceed m, and for proving that p of x greater than equal to m, we have tried to prove many substitute inequalities and intermediate inequalities. So why can we chosen anything large enough? So if I say that all these steps that I am doing are valid only for x larger than both 2 and 6 mod b minus 6b, I will just choose y to be larger than 2 and 6 mod b minus 6. Let's say for example, I will take y to be say 2 plus 6 mod b minus 6b. That is larger than both 2 and 6 mod b minus 6. Okay, so that's why I coined that term, or let's say I didn't coin that term. That term is very frequently used. That is for large enough x, these inequalities hold. Large enough means after some value of x. Can be a very large value, but after some value. So did you get why it is sufficient to prove for x greater than equal to 2 and x greater than equal to 6
Yes.
mod b minus 6b? Okay. The gist is we just need some y, not the optimal y. So let's go over to the previous slide once. So now we have proved that this statement is true. That x power n plus 1 by 2 plus b times x power n minus 1 greater than equal to x power n plus 1 by 3 for large enough x. How large? That is, you need x greater than equal to 2 and x greater than equal to 6 mod b minus 6, which you are free to choose. And how did I arrive that at 6 mod b minus 6b will work for proving this inequality? Just backtracking. That is, I transferred x power n plus 1 by 3 this side and then did some manipulation and arrived at this. Now, the only way to master this kind of backtracking is keep on doing backtracking as much as possible. I mean, practice backtracking, in fact. So this backtracking is very useful in real analysis and calculus. So it's useful to know this. I did not use calculus or real analysis here, but I'm just teaching you how the proofs of analysis and calculus generally go. So now that we have proved this, in order to prove this previous inequality, all we have to do is to prove that this x power n plus 1 by 3 is lower bounded by m by n times x minus 1 for large enough x. So did you get this argument that what we are trying to do? We want to show that a is greater than or equal to c. We instead show that a is greater than or equal to b and b is greater than or equal to c. Here our a is this x power n plus 1 by 2 plus blah blah blah, and c is m by n times x minus 1, and b is that x power n plus 1 by 3. So do you get this argument, this transitivity argument, let's say transitivity of inequalities? Okay, so let's prove that one now. Let's prove that x power n plus 1 by 3 is lower bounded by m by n times x minus 1 for large enough x. How do we do that? Again, we take our freedom for granted and we upper bound x minus 1. So we are taking a lot of things for granted. The fact which we are taking for granted is that for large enough x. So x can be 2 billion, 3 billion, anything. That's why we will just keep on upper bounding and lower bounding as much as we want. So again, we want to simplify the expression. So let's upper bound x minus 1 by x squared. So this inequality is true for all x, not just for x greater than or equal to 2 or 6 mod b minus 6. X squared greater than or equal to x minus 1. This one I think all of you can prove is true for all x, right?
Yes, Dada.
Okay, so how do you prove this? How do you approach this? Write it in the chat that how do you prove that x squared is greater than or equal to x minus 1 for all x? I mean, this inequality is a little bit, too easy to I said for all x, so negative values of x and all that, you can't apply AMGM here. Okay, for this proof we don't need negative values. Positive will work, but I'm asking that can you prove that for all x squared is greater than or equal to x minus? This division by x is not allowed in the first place because x can be 0, can be negative. Transpose 1 and x. Okay, so if you transpose, what do we get? X square minus x plus 1 is greater than or equal to 0. How do you prove this? That x square minus x plus 1 is greater than or equal to 0? I mean, using just basics. You don't need to know any inequality to prove it. How do you show this? This one, all of you should be able to do. I mean, at least without knowing anything about discriminant or quadratic equation or anything. You don't need discriminant or calculus to do this. Okay, so let me ask a simpler question. How do you show that, say, x square minus 2x plus 1 is greater than or equal to 0? How do you
X
show
minus
this?
1 whole square.
Yeah. So how now using this motivation, how do you show that x square minus x plus 1 is greater than or equal to 0? Complete the square. Complete the square and tell me how it is done. Okay, complete the square and tell me what the expression is. I mean, it's not a square, but it will be a sum of squares or something like that. And y is x cube minus 1 by x minus 1 is greater than or equal to 0. So as I said, dividing by x is not allowed. 2x square minus 2x plus 2 greater than or equal to 0. And then next step, So, okay, so that's how we got it. Right, nice. So 2x square minus 2x plus 2 is greater than equal to 0. Yeah, and the second one also, that is x minus half whole square plus 3 by 4. So many ways are there. So either you bring the 2 in the coefficient of x, or you bring a half. So any one of them will work. So why I said this is because instead of knowing that discriminant of a quadratic is this b square minus 4ac and minimum is attained at x equal to minus b by 2a, these are just theorems, but how you arrived at them is important. Okay, so don't memorize them, because differentiation, yes, differentiation also does it, and differentiation makes life a bit too easy. But if you are using calculus at all, then there is no point of doing all these inequalities. Using calculus, this entire 6-page long proof is just 2 lines, I think. So no differentiation allowed. So this is good enough. This 2x square minus 2x plus 2 and x minus half whole square plus 3 by 4. Both of them are good enough. So keeping it to the basics, no calculus. So what I was saying is this is true for all x. You can show this by completing the square. So again, we apply that transitivity strategy that we want to prove a is greater than equal to c. So we want to prove that a is greater than equal to b and b is greater than equal to c. That will make our life easier. So a right now is the left hand side x bar n plus 1 by 3. C right now is the right hand side m by n times x minus 1. And b is that intermediate term which we are going to introduce. It is m by n times x square. So what we'll prove is x bar n plus 1 by 3 is greater than equal to m by n times x square, and m by n times x square is greater than equal to m by n times x minus 1. One of them we have already proved. X square is greater than equal to x minus 1. M and n are both positive, so multiply m by n both sides. Then you get m by n times x square is greater than equal to m by n times x minus 1. The only thing that is left to prove is this, that is x bar n plus 1 by 3 is greater than equal to m by n times x square. So now this part is very simple. Just divide by x square both sides. This is allowed because now we are assuming x to be greater than equal to 2 and 6 mod b minus 6b. So x is positive at least right now. So divide by x square, and you want to prove that x bar n minus 1 is greater than or equal to 3m by n. And this is easy. Choose x greater than or equal to 3m by n power 1 by n minus 1. So what I'm saying is x greater than equal to 2, x greater than equal to 6 mod b minus 6b, and x greater than equal to 3m by say a n power 1 by n minus 1. So for these assumptions, the inequalities that we wanted to prove will hold. So now tell me if all of you get this argument. This part is a little bit confusing, I think. So do you get this argument, what we did just now? So one person has replied, so everyone should reply. Want to prove that x bar n plus 1 by 3 is lower bounded by m by n times x minus 1. We have proved that m by n times x square is greater than equal to m by n times x minus 1. And now we have to prove that x bar n plus 1 by 3 is lower bounded by m by n times x square. Very simple, divide by x square and choose x greater than equal to the value that you want. So now see what we have proved. So we have started with trying to prove p of x is greater than equal to m for sufficiently large x. And in order to prove that, we derive many intermediate inequalities which we proved on the way. And at the end, we have got that for x larger than 2, 6 mod b minus 6b and 3m by n times 1 by 3m by n power 1 by n minus 1, all these intermediate inequalities will hold. And that's why p of x will be greater than equal to m for large x. So Are all of you comfortable with the proof? Let me go over to the initial slide where we started off trying to prove. So we were trying to prove that P is not lower bounded by any real number, and we chose positive real number M, and we have proved that P is not lower bounded by M for sufficiently large X. So only 2 people replied. So everyone should reply, because you know that this proof is difficult. So not everyone will understand at first glance. So okay. So let's generalize this result a little bit. What did we do for so long? We have considered a non-constant polynomial P, and we wanted to prove that P is not lower bounded by P is either not lower bounded by any real number or not upper bounded by any real number. Now I said that let us focus on the case when leading coefficient is positive, and for positive leading coefficient, we will prove that P is not lower bounded by any real number. So case 1, if leading coefficient is positive, then the main thing that we proved in the previous slide is that P of x is greater than equal to M for any positive real number n, and hence P of x is greater than equal to M for any real number m. Now, we will generalize this a bit more. I will state you the generalized results, but since I have told you the proof for one particular result, I can expect that all of you can repeat the same proof for the other results also, because the other results proof are exactly similar. Little bit of change in sign and this and that is there, but otherwise it's completely the same. So 2 cases, if degree is even, then for some y, p of x is greater than equal to m if x greater than equal to y, and for some z, p of x is greater than equal to m if x is lesser than equal to z. So what is this statement telling us? It tells us that if you want to exceed m, then either we have to go very far to the right or very far to the left if the leading coefficient is positive and degree is even. Let's take for example, to enhance our intuition, let us take for example p of x equal to x square. This satisfies the condition leading coefficient is 1, which is positive, and degree is even. Suppose we want to exceed m, where m is equal to say 1. So I'm sure all of you know how the graph of x square looks, f of x equal to x square.
Yes, Dada.
So how does what is the name of this graph? You know the
Parabola.
name? It's a concave up parabola. Concave up parabola, not upward. Concave up. Okay. Concave up parabola, or some say convex parabola, but it's a little bit confusing to say convex and concave and all that. So I prefer saying concave up and concave down. So this is concave up parabola. So if you draw the line y equal to 1 on the plane, then observe that the graph exceeds the line for x greater than equal to 1 and x lesser than equal to minus. And you can prove it algebraically also, that for x greater than equal to 1, x squared is greater than equal to 1, x lesser than equal to minus 1, x squared is greater than equal to 1, and anything in between, it is lesser than 1. So do all of you follow the argument that for f of x equal to x square and m equal to 1, why this is true? Okay. So this result is even more general. That is, if you want to say exceed a real number m, any real number, and you have a polynomial p with leading coefficient positive and degree even. So graphically, if you try to understand, basically the graph doesn't look like a concave parabola, but it resembles many properties of this concave parabola. Like for example, when you go very far to the right, the graph goes to infinity, and when you go very far to the left, again the graph goes to infinity. That is, for sufficiently large x, p of x will exceed m, and for sufficiently negative x, p of x will exceed m. Or more rigorously, what is written here is, for some y, p of x is greater than equal to m if x greater than equal to y, and for some z, p of x is greater than equal to m if x is lesser than or equal to z. So what we proved in the previous slides is this first statement, that is for some y, p of x is greater than equal to m for x greater than equal to y. We proved it for all degrees. We are considering for degree even now. So the other part is easy to prove, that p of x is greater than equal to m for some x lesser than equal to, for some z, for some z, p of x is greater than equal to m for x lesser than equal to z. So this proof you will do on your own based on the proof of the other statement. Okay, so that's one part. The other part is, there is a real number k such that p of x is greater than equal to k for all x belongs to R, which means that p of x is lower bounded. Polynomial with leading coefficient positive and degree even is lower bounded. So to get an intuition, consider again f of x equal to x square. X square is lower bounded by 0. If you don't like 0 because it's a very special case, let's say consider x square minus 1. Again, leading coefficient positive and degree even. It is lower bounded by minus 1. So in general, a polynomial with leading coefficient positive and degree even will have this property. That is, there is a real number k such that p of x is greater than equal to k for all x belongs to R. Graphically, what this means is, there is a certain line y equal to k such that the graph will always stay above that line. So these are the results that we have for degree even and leading coefficient positive. And the second result also you can prove using the first result and a little bit of algebraic manipulation and all that. Just follow the previous. Now for degree odd, again, let's try to predict what is possible. Like previously, we took examples of x square and x square minus 1. So for degree odd, let us take an example and try to predict what kind of limiting values we get. Leading coefficient positive and odd degree. One such example is f of x equal to x. Very simple example. So does f of x equal to x have an upper bound? Answer in the chat. Does x have an upper bound? F of x equal to x. No. Does it have a lower bound? Doesn't have a lower bound either.
Because it
Upper bound
evolves from minus infinity to infinity.
Yeah, so that's what it means. I mean, minus infinity to infinity is the intuition. So that is the rigorous statement. That is, it doesn't have upper bound and lower bound. It's from minus infinity to infinity, correct? No upper bound and no lower bound. And even stronger statement, it exceeds any real number after some point. Not just that p of x is greater than equal to m for some x. P of x is greater than equal to m for x greater than equal to n. So for x sufficiently large, p of x will be greater than equal to m, and similarly for x sufficiently small, p of x will be lesser than equal to m. So now if we try to generalize the result to any polynomial of positive leading coefficient and odd degree, we get this statement. For some y, p of x is greater than equal to m if x is greater than equal to y, and for some z, p of x is lesser than equal to m if x is lesser than equal to z. It's just like f of x equal to x. It will exceed m after some value and it will become less than m before some value. You imagine the graph, and if you draw the line y equal to m, you will observe that after some value, the graph lies above y equal to m. And before some value, again the graph lies below y equal to m. So, do you understand that how the graph of these polynomials look like? That positive leading coefficient and degree odd and degree even polynomials? Okay. So that is the graphical intuition and this is the rigorous statement. So these statements are generally proved, as I said, using calculus, and using calculus there are 2 or 3 lines proof. So I avoided all those hardcore machinery for this one. But really what I'm doing here is just decoding the proof of calculus, just using the definitions and decoding the definitions to get it back to some basic results and all that. So again, since we did for positive leading coefficient, we will have statements for negative leading coefficient also. And it is easy to guess what the statement for negative leading coefficient will be. Because if P has a negative leading coefficient, then minus P has positive leading coefficient. So at least you can conjecture that all the inequalities will get reversed.
Yes, even if we look the graph, we can determine.
Yeah. So, but how do you draw the graph first? Graph is okay. Your intuition is saying that this is true, but then in order to prove that the graph looks like that, you need all this algebra. I mean, you need to prove that for sufficiently large x, f of x will exceed m, and for sufficiently small x, it will not exceed m or exceed m, something like that. Not to conclude that the graph looks somewhat like that. Okay. So when you do maths, you have to be careful that what you are, when you are succumbing to your intuition and when you are actually doing a rigorous proof. Like you might say that okay, it's almost always the case that the intuition works. Then why not always do using the intuition? But the thing is that when you do, much higher branches of maths, that time intuition will fail. Not just maths, even in physics, there are some things where intuition will fail. So, like for example, I'll give you just a very live example of how intuition can fail in maths. There is a paradox called Banach-Tarski paradox. I'm not sure if you have heard of this Banach-Tarski paradox before. Basically, the idea is, in layman's term, it means that suppose you have a ball of some radius. Okay, it's a hypothetical ball. No need to consider mass and density and all that. So the question is, can you cut up the ball into a finite number of pieces and rejoin them in order to get two balls of that same size? There is no question of changing the density or anything like that here. It's just about volume. Okay. So your intuition says, or let's say your physical intuition says that, uh, well, how is it possible? Your volume is not getting conserved, and you, let's say, consider all the densities to be one, then mass is not conserved, and all that is happening. But the thing is that it is your intuition saying that, and when you try to write it down rigorously, the problem that occurs is conservation of volume is a difficult thing to explain, because defining volume itself is a bit difficult. When you will learn probability or say measure theory, you will see that a lot of research has been done how to define volume for arbitrary set. And it turns out that when you actually cut up these pieces, I mean, there is a way to cut up the ball into pieces in such a way that the volume becomes undefined. So this question of conservation of volume is thrown out of the window. There is no volume itself. There is no question of conserving volume.
But the answer will be that the two wells cannot be made after cutting, right?
No, the answer will be they can be made. Okay, so it is non-intuitive. Even I don't know the proof right now. I don't know
But
the
how about
theory.
you suppose if we take the first one of the volume, suppose it's 2 wall 4
Yeah,
by
that's what I am saying. You are talk just now
no,
I
yeah,
said,
just
and you
one.
are
If
making
we
the
take
same
that
mistake.
4 by 3 pi r1 cube plus 4 by 3 pi
Yeah, that
r2 cube
that
equal to 4.
thing. Okay, so that is the volume of the ball.
Then r1
What
cube
is the
plus
volume?
r2 cube equal to r3 cube. That's not possible.
Okay, so let me ask you that when you cut up, what is the volume? Initially, the volume is 4 by 3 pi r cube. But when you cut up, what is the volume? Let's say
Okay, I got it.
if I give you a very Bezier set, I don't know if you have heard of this set. If you have heard of Cantor set, have you heard of Cantor set?
No, Dada.
A Cantor set is basically the set of all real numbers between 0 and 1, which in their decimal expansion have, okay, not decimal expansion, sorry. In their binary expansion, they have only zeros and twos in them. Okay, okay, I'm making a mistake again, not binary, sorry. Ternary expansion, I keep forgetting the terms again. So Cantor set is a set of all real numbers in closed 0, 1 such that their ternary expansion, and I find it difficult to remember these terms, ternary expansion have only say zeros and twos. Ternary expansion consists of zeros, ones, and twos. So Cantor set is that set for which you have only zeros and twos, and between 0 and 1. But there is a more intuitive construction of the Cantor set, and that also explains why this concept of volume and length are all difficult. Very simple. Is first, let's say, take the interval, closed interval 0, 1, and remove 1 by 3, 2 by 3 from there. That is basically you divide it into 3 parts, 3 equal parts, and remove the middle part. And do the same again for 0, 1, 1 by 3, and 1 by 3, 2 by 3. That is from each of them. For each of them, let's say you take 0, 1 by 3, divide it into 3 equal parts, remove the middle part. That is from 0, 1 by 3, remove, let's say, 2 by, let's say what parts we get. If we divide 0, 1 by 3 into 3 parts, you will get 0, 1 by 9, then again 1 by 9, 2 by 9, and 2 by 9, 3 by 9. So remove this 1 by 9, 2 by 9 from 0, 1 by 3, and then you are left with 0, 1 by 9 and 2 by 9, 3 by 9. And do the same with 1 by 3, 2 by 3 also. Remove the middle part. And you keep on doing this. The Cantor set is defined as the limiting set. Now, limiting set basically, rigorously, it means the intersection of all the sets that you got. So intuitively, you can understand what we are doing is we are removing the middle third, and we are continuing this infinitely many times. Now, it turns out that this set is very interesting. It has many nice properties, and it's also useful in real analysis. Now, even for this bizarre set, you have a definition of length. Like for a normal interval, like say a comma b, at least you can define the length to be p minus a. But for this kind of a weird set, how do you define the length? So a lot of theory is there for how to define length and areas and volumes for bizarre sets. So basically, when you are actually cutting up the ball in that Banach-Tarski paradox, when you cut it up into say 5 pieces, you have to define the volume for each piece, and the pieces can be very bizarre if you want. I mean, there is no constraint on how you have to cut up. You just need some constraints on how many pieces you can make, but not exactly how the pieces have to look like. It can look very crazy also. It can look like a fractal or something like that, if you have heard about fractals and all that. So you have to define volumes for them. And the thing is, the moment you talk about conservation of volume, your argument goes wrong, because volume isn't even defined for some sets. And that's why this proving the negation is not possible in that case. Indeed, it turns out it can be proved that it is possible to cut up one ball of say radius 1 into some number of pieces with some constraint, such that if you rejoin the pieces, you can make 2 balls of radius 1. So basically, it's a very confusing thing. So there is one case where intuition fails. There are many other cases also. So again, in physics, you have things like gyroscope and all that. So when you learn about say multi-axis rotation, at one point you will think there is no way that how the gyroscope is staying upright. But the thing is, the normal reaction force is acting in such a way that the gyroscope does stay upright. So these are all bizarre things. Your intuition will fail many times in science. That's why these proofs are necessary. So always resorting to graph is not an option for us. We have to prove that why the graph looks like the way it does. So we prove for positive real values, positive leading coefficients, and now let's see the result for negative leading coefficients. If the degree is even, so what should it be? For some y, p of x is lesser than equal to m if x greater than equal to y, and for some z, p of x is lesser than equal to m if x is lesser than or equal to z. Okay. So let's take for example, if you consider p of x equal to say minus of x square. Again, I'm resorting to intuition now to explain to you, but again, proof you have to do on your own based on the idea that I showed you. The graph looks like a concave down parabola. So if you consider, let's say, a real number like y equal to -1, and you consider that line y equal to -1, then the graph will lie below y equal to -1 after some value of x. Let's say after x greater than equal to 1. And again, before x lesser than equal to -1. So when you go very far to the right, it goes below. When you go very far to the left, it again goes below. And in between these two extremes, you have something which is greater than 1. And again, the second part is there is a real number k such that p of x is lesser than equal to k for all x belongs to real numbers. And minus x square is upper bounded by 0. And let's say minus x square plus 1, that is upper bounded by 1. So now let's consider odd degree. For the odd degree, the results are very similar to the previous slide statement also. Let's say p of x equal to minus x, negative leading coefficient and odd degree. So what do we expect? We expect that p of x becomes lesser than or equal to m for large values of x. That is true. It looks like a straight line slanted towards the left. So if you consider any real number, say y equal to -1, let's say, or m equal to -1, let's say, then for sufficiently large value of x, the graph goes below that real number. And again, p of x is greater than equal to m for x lesser than equal to z. This for sufficiently negative values of x, the polynomial exceeds m, because on the left hand side it is going to infinity. So these are the main results that I wanted to tell you. So if you are not comfortable with any one of those results, you can write in the chat. And one of the results, that is the very first result I have proved for you, the remaining ones you can prove. Okay, I will send the presentation slides today. Correct. So do all of you get the argument?
Yes.
Write in the chat, not okay. So you know a lot of things about polynomials by now. I mean, very powerful results in it. Using calculus, this would have been easy to prove, but without using calculus also you could prove it, and I've shown you the idea. So let us summarize these results and apply them. The gist is that a non-constant polynomial cannot be both upper bounded and lower bounded, and hence a technique to prove that a polynomial is constant is just that prove that it is bounded on both sides. That will do the job. So you have a polynomial p, you are asked to prove that p is constant, and say sometimes you are given some bounds on the size of the polynomial. Then it is immediate that you have to think about how to consider the limits of the polynomial. If it is constant, it will be bounded on both sides because it's just one number, right? But if it is not constant, non-constant polynomial, that is degree at least one polynomial, then it won't be bounded on one of the sides. So if you have to prove that it is constant, all you have to do is show that it is bounded on both sides. And again, say you have to prove that it is 0, then first prove that it is constant and then prove that that constant is 0. So let's see how we can exploit this idea. Can you send the calculus proof in the group or just discuss how it is done? So the idea is simple, just factor out x power n just as we did in the first step, and then take limit as x tends to infinity. I mean, if you know calculus, then this proof should be obvious. This, after the first step, the proof is obvious. So I am writing in the chat for doing using calculus. Factor out the largest power. Factor out x power n. Then take limit as x tends to infinity and minus infinity. basically what you will get is that x bar n is the dominant term and the remaining terms all go to 0. And what matters is the leading coefficient and the degree. So that's the sketch of proof. And after this, if you actually have done limits, this should be easy for you. Okay. So what we were saying is that to prove that a constant, prove that a polynomial is constant, we will show that it is bounded on both sides. And to prove that it is 0, first we'll prove that it is constant, then prove that that constant is 0. So here is a question from Harvard MIT maths tournament. I was too lazy to type it out. That's why I just took a screenshot from the PDF and posted it in the PPT. Forgive me for that. The question is, let Px and Qx be non-constant polynomials with real coefficients. If it is given that that box of Py equal to box of Qy for all real numbers y, so I hope you know that what is meant by box of Py.
Yes, the nearest integer.
Not nearest integer. It is not the nearest integer. Greatest integer function, that is a name. What does it do? Explain what is meant by greatest integer function if you know it. Or if you don't know, then I will tell.
It is the greatest integer lesser than or equal to the given real number.
Correct. So can't see the question. So why can't you see the question? Is there a
Other it's visible, maybe some problem with his or her internet connection.
okay? So meeting ends in 5 minutes. I will just take 1 minute to say the definition. Greatest integer function is that the largest integer lesser than or equal to a given real number. A box of 3.2 is 3. Box of 3.5 is again 3. Box of 4 is 4. You go to the real line, consider the set of all integers before that number and consider the largest. Okay, so end the meeting, Kwane. I will continue in the next one.
Dada,
Yeah,
there was one question. Can I ask you?
yeah, ask it now till the
There,
others join.
there was one
Okay.
question. If Px denotes a polynomial of degree n such that Pk equal to 1 by k for k equal to 1, 2, 3 till n plus 1, determine P of n plus 2. But in
Yeah.
this, if we declare a function, then the declared function is becoming the zero polynomial because it is becoming zero for n plus 1 values.
Yeah. So
How will we do it then?
which polynomial is becoming the zero polynomial? Which function is becoming the zero polynomial?
It's given pk equal to 1 by k. Suppose I declare a function gk equal to pk
Write
minus
in the chat. Write it in the chat. Then it is easier to understand the function.
Okay.
So where did you go? You write the function in the chat which you were talking about.
Okay, Dada.
Not WhatsApp chat, this chat.
Yes, Dada.
So what function did you take?
I take gk equal to pk minus
Write in the,
k.
write in the chat. I'm saying. Write the function in the chat, not the question. Question is obvious here. You don't need to write the whole statement. Just write one or two words. It will be enough. Okay, so that is not a polynomial. Cannot apply theory of polynomials in p of x minus 1 by x. You need a polynomial for doing the question. How do you get a polynomial? You don't want that 1 by x hanging around, right? In that inequality. In the equality. How do you remove 1 by x? Yeah, so simple. Just consider the function x times p of x minus 1 instead of considering p of x minus 1 by x. Did you get the idea? You need a
Yes,
polynomial.
yes, Dada.
So you know the polynomial now, x p of x minus 1 that has degree n plus 1. And you know n plus 1 values of that polynomial. So now you have to think that what we can do with that and what not. You might say that, well, in Lagrange interpolation, you said that you need more values or less values or something like that. But thing is that you cannot forcibly apply Lagrange interpolation everywhere. Sometimes you just have to use the idea of Lagrange interpolation. So, or even if you want, you can do using Lagrange interpolation, but there will be one extra term hanging around which will get cancelled somehow and something like that will happen. So back to the question at hand. What were we discussing? So seeing the screen. So I hope all of you have got the definition of greatest integer function. P of x and Q of x are two non-constant polynomials with real coefficients such that box of P of y equal to box of Q of y for all real numbers y. Then you have to prove that P of x and Q of x are identical. Here box of x denotes the greatest integer lesser than or equal to x. Like one example is given, box of minus 3.14 is minus 4. If you don't see how this is true, just draw the real line and mark the integers on them and consider the greatest integer lesser than or equal to y. Okay, so how do we go about proving this based on the previous discussion, based on this limits discussion? I won't discuss the full proof now. Just
Can we assume a polynomial f of x equals to p of x minus q of x?
yes. So what do you want to prove about that polynomial?
We can substitute p of x equals to greatest integer of p of x plus fractional part of p of x. Then f of x equals to p of x minus q of x equals to fractional part of p of x minus fractional part of q of x. Now we see that they are bounded between 0 and 2. So f of x is a constant polynomial.
Yeah, 0 and 2. No, I don't think 0 and 2 it is.
No, the fractional part of p of x minus the fractional part of q of x is bounded between 0 and 2. So it is a constant polynomial.
Fractional part of p of x and fractional part of q of x is bounded between 0 and 2. Why it cannot be negative?
Fractional part of p of x minus fractional part of q of x.
Yeah, so if fractional part
Oh,
of
it is
p
bounded
of
between
x
minus
is
1,
smaller than
minus 2 and 2. Yes, I think so.
minus 2 and 2 as well as minus 1 and 1 will also work. Okay. So you can say that that the absolute difference is bounded between 0 and 1 because fractional part is always between, yeah, so fractional, yeah, correct. So p of x minus q of x is equal to fractional part of p of x minus fractional part of q of x, which is bounded between, I mean, whose magnitude is bounded between 0 and 1. So what do you conclude about p of x minus q of x? It is very easy. Just now I said the idea. Polynomial is very
It is a
good.
constant
Polynomial, everything
polynomial.
is a polynomial. Huh?
It is a constant polynomial.
Yeah, so p of x minus q of x is a constant polynomial. So now the only thing that you have to do is you have to prove that the constant is 0. So, okay, I won't exactly tell you that how to prove that the constant is 0. Okay, do you get any? I just used my start taskbar now. Is the screen getting blocked or something?
Yes, Dada. A
Now is
box.
it getting blocked? Has it gone?
No, Dada. Still a gray box.
Every time I check the time, it is going to block this. Wait for some time till it is gone. I have turned off my.
Suppose p of x is an
Okay, before that,
integer.
is the screen still blocked before going the question?
No, it's
Has it
not
gone?
blocked.
It's not blocked,
I
it's
can
gone, right? Now blocked again, or is it gone?
Now it's gone.
Okay, thank God. So what we were saying is we want to prove that that constant is p of x minus q of x is equal to a constant, and we want to show that that constant is 0. So basically, the idea that I have in mind right now is to prove by contradiction. That is, if I can show that if it is non-zero constant, so let us assume that it's a positive constant. For negative one also it will be similar. So if p of x minus q of x is a positive constant, then I want to show that box of p of y equal to will not be equal to box of q of y for some y. What did you say? Let px be? What is that? 1.
I
I. What is I?
in an integer,
Okay.
any integer.
P of x continuity. So continuity I have a solution using continuity, and if you see the graph also you can do, but anyways, okay, let's see what you do. Let p of x will be equal to some integer minus 0.1 k, where k is the constant. Very nice. Then you are saying that p of x and q of x do not have the same latest integer lesser than equal to that number. Is that what you are saying?
Yes.
Okay, so the intuition is basically correct. So mainly what you have to do is you have to imagine the graph. So when say p of x is equal to this, say some integer minus 0.1 times k, and this q of x is k apart from that, it goes all the way to the previous interval. So that's why this won't be true if that constant is not 0. So this is the idea. Now I didn't mean to give away the solution or anything, and anyways, if you can find out a solution without using continuity is very nice. In fact, I don't think you exactly need continuity or something like that. Anyways, I won't tell you the remaining solution. If you cannot at all do without using continuity or anything, just imagine the graph of the polynomial. Okay. So if you imagine the graph of p of x, this continuity thing becomes obvious. So since you have done the graph, I thought that you could at least get the idea of continuity here. So mainly that is the technique. You have to assume that p of x is equal to some integer minus 0.1 k. For some integer it will be true, and from there you can do it. So do the proof on your own. Even if this solution is not clear to you, you should be able to do on your own. Okay, so let's go over to the other idea, that is another useful conclusion is that from the previous discussion, that if the leading coefficient of a non-constant polynomial is positive, then we can make it an arbitrarily large positive number for sufficiently large x. What do I mean by that? If you are given, say, m, positive real number m, you can make px larger than that m by considering x greater than equal to y for some y. That is what is meant by we can make it arbitrarily large positive number for sufficiently large x. Similarly, if the leading coefficient is negative, then we can make it an arbitrarily large negative number for sufficiently large x. So I hope all of you follow these last two conclusions. Cannot see your screen. Is it blocked by any gray box or something? Because I didn't use the. Okay, so let's see what I can do for you. I will just start sharing once again. Okay, so now can you see everyone? Okay. So do you follow the last conclusion that for a polynomial with positive leading coefficient, we can make it arbitrarily large positive number for sufficiently large x, and for a polynomial with negative leading coefficient, we can make it arbitrarily large negative number. By arbitrarily large, I mean you can arbitrarily large negative. I mean you can make it say less than -1, -2, -1000, -1 billion or whatever. Arbitrarily large negative number for sufficiently large x. Okay, so this idea is what we are going to use next. So everyone should reply to this. Can everyone understand this conclusion? Okay, so we are going to apply this idea. Now next question, which I'm going to solve completely for you, because okay, not completely, maybe one small part I will leave it to you, because It's not really related to the theory that we have done, but can be done. So this question is from Canada 2010. Let P of x and Q of x be polynomials with integer coefficients, and an be equal to n factorial plus n for all natural numbers n. So we are considering a sequence of natural numbers. Now, obviously you have to assume that Q of n is non-zero for every n. Now consider P of n by Q of n. If it is given that this ratio is an integer for all positive integers n, then you have to show that P of n by Q of n is an integer for every integer n not equal to 0. Okay, so the question is, if P of n factorial,
So we can take this for granted that P of an by Q of an will be an integer for every positive integer.
yeah, that is what is given to you. Integer for every natural number n, factorial you have not learned how to define for negative ones. It can be defined, but you have not learned yet. So for every natural number n, then you have to show that P of n by Q of n is an integer for every integer n not equal to, for every integer n such that, sorry, Q of n not equal to 0. There is a small mistake here. Q of n should be non-zero. Okay.
Yeah. Can we do it like this? Suppose the integer be I, we can p of an minus I multiplied by q of an is equal to 0. Now,
Yeah. But that I is a function of n.
yeah. This is another polynomial of a
No,
finite
it is not.
of a
It is not another polynomial. It's
no
not
p of
another
an
polynomial function of x or whatever. I mean,
from a polynomial function of an. It's a
it is not a polynomial function of n. It is not necessarily a polynomial function of n, because that I is also depends on n. I is not a constant here. Not the same integer. I am saying it is an integer. Maybe 0, 1, 1000 different integers might be there.
Okay.
Backtrack and use contradiction. Like, suppose P of n. I'm not sure how you are supposed to backtrack here. Okay. So the first idea is I'm rejecting it. It's not a polynomial. That I be very careful when you are applying what. This I is a function of n, so automatically it becomes dependent on n also. So you cannot say that this thing is a polynomial function of an. Okay, so that's not correct. That idea, I don't think it will work either. I'm not sure. It might work, but in some other, if you do some other manipulation, maybe you can bring. But this one is not a polynomial function. It's p of n minus I times q of n. So how do you think you should backtrack and use contradiction here? That for some n it is not an integer. So what backtracking will you do? What is your idea? So first we assume that p of n minus q of n. No, you cannot assume that. It is given that p of n by q of n is an integer for all natural number n. You have to prove the last part, that is p of n by q of n is an integer for every n not equal to 0. That an thing is given to you. So if you want to use contradiction, you have to assume that for some natural number n, p of n by q of n is not an integer. Or let's say for some integer n, p of n by q of n is not an integer. But there is no guarantee that that n will be equal to some ak. I mean something of the form k factorial plus k. Okay, so think about this and write it in the group if you can prove it using contradiction. But since there is less time, I will give you an idea of how to do it using limits. Okay, so moving on to the next slide, the part that I will leave it to you is the non-monic case. I will do for the case when q of x is monic. Now, the non-monic, I will give you an idea of how to do it for the non-monic case also, but at least that part you have to do on your own. That part is not related to any theory you have done. It is just observation, the non-monic case. For the monic case, let me highlight the idea. First things first, the moment you see two polynomials, always you have to try to reduce the degree of one of them. That's why we have two polynomials p and q. Try reducing the degree. How do you do that? Use division algorithm. Whenever you have two polynomials, immediately apply division algorithm when you are considering the ratio of those two polynomials. It becomes easier. So, the last class I stated division algorithm for integer polynomials. That is, if p and q are two integer polynomials such that q is monic and q is not identically 0. Obviously, q is not identically 0 in this case, otherwise division by q of n doesn't make sense. Then you can find unique integer polynomials g and h such that p equal to q into g plus h, and either h is identically 0 or the degree of h is from 0 to degree of q minus 1. So I hope all of you remember this statement. Okay. So now tell me, if h is identically 0, then is the answer obvious? I mean, is the solution obvious? What happens for h equal to 0, identically equal to 0? Does the conclusion hold that p of n by q of n is an integer for every integer n? G of x is an integer, and why so? Because g is an integer polynomial, that is, it has all integer coefficients, and p of n by q of n will be g of n. So all coefficients are integers, the value we're taking is that is also an integer, so g of n is an integer, that's why p of n by q of n is an integer. So the only case that you have to deal with is this, that is 0 lesser than equal to degree of h lesser than equal to degree of q minus 1. Then from there, dividing by q of n, you get e of n by q of n equal to g of n plus h of n by q of n. Now it is given to you that p of n by q of n is always an integer. And since g has all integer coefficients and an is an integer, that's why g of n is again an integer. Okay, sorry, this should be g of n here. That I have written here h of n is always an integer. This is wrong. This should be g of n instead of h of n. G of n is an integer because g is an integer polynomial and we are inputting an integer inside it. So p of n by q of n minus g of n will also be an integer then. That means h of n by q of n, that thing will always be an integer. Now this is a little bit more advantageous because we know that the degree of h is less than the degree of q. So this kind of allows us to apply the theory of limits. I will show you how. So from the previous discussion, we know that for large n of x, h is either always positive or always negative. Same for q of x. Hence, for large n of x, h of x by q of x is either always positive or always negative. So, do you get this last argument? Can we show that p of n factorial by q of n factorial? Yeah, I mean, using this argument, you are showing that p of n by q of n is always an integer for any n. So, for factorials also. If you mean that from that n factorial plus n statement, you want to arrive at that n factorial statement. Okay, so how do you want to do that? Directly from that n factorial plus n, how do you want to go to n factorial? If you are not sure now, discuss on WhatsApp. I mean, if you are sure, then tell me now. Okay, so basically, okay, so I will prove it using the limiting argument. So what I was saying is, observe that for large n of x, h of x is either always positive or always negative. And for large n of x, q of x is either always positive or always negative. And hence, h of x by q of x is either always positive or always negative. Now, what do I mean by this statement? Let us say, let me discuss one case with you. Let's say if say h is constant, non-zero constant. If h is a non-zero constant polynomial, then obviously that constant is either positive or always negative. That's why h of x will be equal to that constant, and that's why it will be either always positive or always negative. If h is a non-zero constant, if h is non-constant, then what do we do? Then h has either positive or negative leading coefficient. So if we deal with the case of positive leading coefficient now, then in the previous slide I told you that for large n of x, h of x can be made arbitrarily large. So suppose I want to make h of x larger than 1. I can make it by selecting some y such that for x greater than equal to y, h of x is larger than 1. We saw the proof also. So that means after that y, h of x will always be positive also, because if it is larger than 1, it is larger than 0 also. So h of x is always positive for x greater than equal to y. Similarly, if we had negative leading coefficient, then by the previous discussion, h of x can be made, say, smaller than -1 by taking large n of x. That means for large n of x, h of x will be negative. So we can sum it up in this one statement, that is, h of x is either always positive or always negative, not necessarily for all x, but for large n of x. That is, for some, there is a y such that for x greater than equal to y, h of x is greater than 0 for all x greater than equal to y, or h of x is less than 0 for all x greater than equal to y. So do you follow this part of the argument? Okay. The same thing can be said about q of x also. Same idea, just deal with the case when it is non-zero constant, then it is either positive or negative. If it is a non-constant polynomial, then for sufficiently large x, you can make it either always positive or always negative. So I have two numbers, h of n and h of x and q of x. H of x is positive, q of x is negative, then h of x by q of x is negative. If h of x is negative, q of x is negative, then h of x by q of x is positive. If h of x is positive, q of x is positive, then the ratio is positive. If h is negative, q is positive, then again the ratio is negative. So anyways, for large n of x, h of x by q of x is also either always positive or always negative. So do you understand this last statement? That is, if I want to state it rigorously, there is a y such that for x greater than equal to y, ratio is either always positive or always negative. It is, there is no fluctuation. That is, say for y for x equal to y plus 1 it is positive, y minus y plus 2 it is negative. That won't happen. There is a y after which it is, the graph is totally above the real line or below the real line. So Follow the last argument. Okay. So now we want to exploit this. How do we do that? So let's see. Let's deal with the positive case. Negative case is similar. This means that there is a real number y such that for x greater than equal to y, h of x by q of x is greater than 0. So I want to make x greater than equal to y. Here what values of x are we considering? Here we are considering x equal to n factorial plus n. So we want to make this n factorial plus n greater than equal to y. So how do we prove this? How do we get this rather? Observe that if we take any natural number n not greater than equal to y by 2, it is always possible. Y by 2 is a finite number. You can, natural numbers are unbounded. You can always take a natural number greater than equal to y by 2. Then for that n naught, whenever a natural number n is greater than equal to n naught, what can you say about an? An is equal to n factorial plus n, which is greater than equal to n naught factorial plus n naught. N naught factorial is again greater than equal to n naught. That's why the sum is greater than equal to 2n naught, and 2n naught is greater than equal to y. That means for n greater than equal to n naught, an is greater than equal to y. For n greater than equal to n naught, an is greater than equal to y. But if we substitute x equal to an in the first statement, then we get h of an by q of an is greater than 0. So what does this mean? It means that for sufficiently large values of n, h of an by q of n will be greater than 0. How did we prove this? We showed that for sufficiently large x, h of x by q of x is greater than 0. And by making n large enough, we made an larger than y. And that's how we did. So then we get h of n by q of n is greater than 0 for large enough n. So did you get this part of the argument? This how we arrived at this h of n by q of n argument? Okay, so if you did not understand, then write in the chat. I mean, this part is a little bit difficult. Okay, I will explain again. So the first part you have got that for large n of x, h of x by q of x is greater than 0. Now we were dealing with h of an by q of an. So that means to make it fit into this statement, we have to make an large enough. So how do we make an large enough? How do we make an larger than y? So y by 2 is a finite number, finite real number. You can always find a natural number greater than y, greater than equal to y by 2. So take one such natural number, call it n naught. So whenever n is greater than equal to n naught, what happens to an? An is equal to n factorial plus n. But n factorial is greater than equal to n naught factorial because n is greater than equal to n naught. Similarly, n is greater than equal to n naught. So after summing up, you get n is greater than equal to n naught factorial plus n naught. But n naught factorial is greater than equal to n naught because n naught factorial is something like n naught into n naught minus 1 up to 1. So remaining terms are lower bounded by 1. So n naught factorial is lower bounded by n. So n naught factorial plus n naught is greater than equal to n naught plus n naught. And by our assumption, that is greater than equal to y. That means we have made n greater than equal to y. So for n greater than equal to n naught, n is greater than equal to y. And if an is greater than equal to y, then just look at the first expression in the red box. For x greater than equal to y, h of x by q of x is greater than 0. So now an is greater than equal to y, just substitute x equal to an. Then what do you get? You get that h of an by q of an is greater than 0. That means for n greater than equal to n naught, h of n by q of n is greater than 0. That means for sufficiently large n, you have made h of n by q of n is greater than 0. So now, did you get this argument? That what we did just now, we have just now made h of n by q of n positive. We don't want to deal with different kinds of real numbers, we want to deal only with positive real numbers. Okay, so now what are we trying to do? So let me go back to the previous slide and show you that exactly what we are trying to achieve by doing all these limiting arguments. But how do we plan on proving that p of n by q of n will be an integer? So basically, what I want to say is, in this one, focus on these two boxes. If h is identically 0, then we were done. So now we assume that h is not identically 0. How do we plan on doing that? We have to use roots of the polynomial. If h is not identically 0, then it cannot have infinitely many distinct roots. It will have only finitely many distinct roots. So if you want to prove that h is identically 0, all you have to do is create infinitely many distinct roots of that polynomial h. That argument you have seen earlier also. So that is exactly what I am trying to do here. So instead of dealing with h, I am dealing with h by q, right? I am trying to show that h of an by q of an is somehow getting closer to 0 for large n. So how do you show that? That is exactly what I'm trying to do. So what did I show just now? Just now I showed that h of n by q of n is positive for large n. Now I'm trying to show that it is closer to 0. Now just showing that it is positive does not mean it is closer to 0. I have to show something more than that. So I will show that it is less than 1 also for large n. And that will somehow be a contradiction of some sorts, because we assume that h of n by q of n is an integer and there is no integer between 0 and 1. Okay, so I will arrive at that later again, even if you don't understand now. Let me first prove this statement, that is h of n by q of n is less than 1, and then we will see that how that gives us the contradiction. So just keep in mind, what we are trying to show is h of n by q of n goes closer to 0. H of n by q of n is positive for large n. Now we want to prove that h of n by q of n is less than 1 for large n of n. So how do we do that? Again, we will use the limiting argument. So first we need a polynomial for that. If the leading coefficient of q is positive, then for large n of n, q of n is greater than 0. We saw that just now. So let's deal with the case that the leading coefficient of q is positive. So now you can multiply q of n both sides, because q of n is larger than 0 and the sign of inequality will be unchanged. So in order to prove this statement, h of an by q of an is less than 1, you have to show that h of an is less than q of an for large n. But since the leading coefficient of q of n minus h of n is positive, that means q of n is greater than h of n for large n of n. Now, why is the leading coefficient of q of n minus h of n positive? That is because degree of h is less than the degree of q. So the leading coefficient of q minus h is same as the leading coefficient of q. That is positive. That is our case 1. So q of n minus h of n also has positive leading coefficient. That means for large enough n, we can make q of n minus h of n positive. So that does the proof, because if q of n is q of n minus h of n is greater than 0, then you get q of n is greater than h of n. Then again q of n is positive for large n, so divide by q of n and you get h of n by q of n is less than 1. So did you understand this first case, the first part of the argument? So more people should answer again. This is a difficult part, I know. So if you're not clear, please write it in the chat. I will explain again. If you are not clear, then also write in the chat that you are not clear. Then I will go over the explanation again. Only two people, more people are there, I guess. So I want to prove that h of n by q of n is less than 1 for large n of n. Case 1 is when leading coefficient of q is positive. I am dealing with that case. So for large n of n, q of n is greater than 0, because for large n of n will be very large, and for large enough values of x, we saw that q of x will be greater than 0. That's why q of n will be greater than 0 for large n. Hence, just multiplying q of n both sides, we have to show that h of n is less than q of n for large n. But then consider the polynomial q of n minus h of n, whose leading coefficient is same as the leading coefficient of q, and hence positive. So again, from the theory of limits, we see that for large n of n, since an is very large, that's why q of n minus h of n will be positive. Meeting ends in 5 minutes. Okay, restart the meeting. I mean, if you won't be able to finish the argument here, anyways. Restart the meeting. Okay, so I'll go over the whole argument and you can see the recording later. Is we want to prove that h of n by q of n is less than 1 for large enough n. Now, we deal with one case when the leading coefficient of q is positive. And just now we saw that for large enough values of x, q of x is greater than 0. And again, for large enough n, an can be made arbitrarily large. And hence, if you substitute for large enough n, q of an will be greater than 0. So I'll write down the rigorous argument in the chat. That is, there is a y such that q of x is greater than 0 for x greater than equal to y. And there is an n naught such that an greater than equal to y for n greater than equal to n naught. Then substituting, we get for n greater than equal to n naught, q of an is greater than 0. And to prove the inequality h of n by q of n is less than 1, we can just multiply q of n both sides because it is positive. That means we want to show that q of n is greater than h of n for large n. Now consider the polynomial q of x minus h of x. Again the same argument. Now the leading coefficient of q of x minus h of x is same as the leading coefficient of q because the degree of h is less than the degree of. So leading coefficient of q is positive and hence the leading coefficient of q of x minus h of x is positive. That means for some y, or let's say for some z, when x greater than equal to z, q of x minus h of x is greater than 0. And again, there is an n1 such that for n greater than equal to n1, an is greater than equal to z by a similar argument as before. Then substituting again, we get q of an minus h of an is greater than 0 for n greater than equal to n naught. That means for sufficiently large n, q of an minus h of n is greater than 0, and that is what we wanted to prove. This shows that h of n is less than q of n, and by dividing by by dividing by q, we get h of n by q of n is less than 1. Similarly, if the leading coefficient is negative, then q of n is less than 0 for large n. Similar argument. Then by multiplying q of n both sides of the first inequality, that is h of n by q of n less than 1, that is what we want to prove. We have to show that h of n is greater than q of n for large n. But again, consider the polynomial q of x minus h of x, whose leading coefficient is same as the leading coefficient of q. That's why, by the same argument as before, we see that since the leading coefficient of q of x minus h of x is negative, so q of n minus h of n is indeed less than 0 for large n. Hence, q of n is less than h of n, and by dividing by q of n, we observe that h of n by q of n is less than 1. So what did we prove now? We proved that for large n of n, h of n by q of n is less than 1. There is a t such that, oh, not t, sorry, let's say we need a natural number. There is an n2 such that for n greater than equal to n2, h of an by q of an is less than 1. That means for large n of n, h of n by q of n is less than 1, no matter what the leading coefficient of q is. But in the previous slide, we showed that for large n of n, h of n by q of n is greater than 0 also. So we get two inequalities. H of n by q of n is less than 1 and h of n by q of n is greater than 0 for large n. But in the first slide of this solution, we made an assumption. What did we assume? Here, we were dealing with the case when 0 lesser than equal to degree of h lesser than equal to degree of q minus 1, and we said that since p of n by q of n is always an integer and g of n is always an integer, and hence h of n by q of n is always an integer. But just now we have proved that h of n by q of n lies between 0 and 1 for large n of n. That is a contradiction. So I'll write it in the chat. H of n by q of n is always an integer, but for large n of n, that is for n greater than equal to k, for some k, h of n by q of n lies between 0 and 1, and that is a contradiction because there is no integer between 0 and 1. So what did we contradict? Our first assumption, the assumption that the degree of that h is non-zero, that's why 0 lesser than equal to degree of h lesser than equal to degree of q minus 1. Based on this assumption, we arrived at the fact that h of n by q of n is always an integer because that is equal to p of n by q of n minus g of n, and those are integers. That's why the ratio h of n by q of n is always an integer. But using limiting argument, we showed that h of n by q of n is positive for large n and less than 1 for large n. That's why for large n of n, h of n by q of n lies strictly between 0 and 1. But then there is no integer between 0 and 1, and that gives us a contradiction. So our assumption that there is a degree of h which is 0 lesser than equal to degree of h lesser than equal to degree of q minus 1, that assumption is wrong. So the only other possibility is when h is identically 0. That's why we have proved that in this division algorithm statement, the a's that we get will be identically equal to 0. And that solves the problem, because then p of x will be equal to q of x times g of x. And hence, you will get that p of n by, sorry, not p of n, p of x by q of x equal to g of x. And in this, if you substitute x equal to n for any integer n, then p of n by q of n equal to g of n, which is an integer because g has integer coefficients and you are substituting an integer. And that solves the problem. That for every integer n, p of n by q of n is an integer. So that is how we applied the limiting argument here. We assume that the remainder polynomial is non-zero, and using the fact that it's an integer, we showed that it lies between two real numbers for large n, and between those two real numbers there cannot be any integer. So it gives us a contradiction. So all of this we proved making some assumptions. So let's go over that again. So somewhere we assumed that this is the positive case that we are dealing with. Where did we assume that? Let's see the previous slide. In the first slide, we assume that for large n of x, h of x by q of x is either always positive or always negative, and we said that we will deal with the positive case first. And from this positive case, we arrived at the conclusion that h of n by q of n always lies between 0 and 1. So similarly, for the negative case, we will get that h of n by q of n always lies between 0 and -1 for large n of n. And that again will give us a contradiction in the same way. So basically, for both positive case and negative case, we have proved the statement. Then again, in the beginning, we had made another assumption that in the question we had q and we had assumed that q is monic, but the monic case the monic had never been stated in the question. So how to deal with the non-monic case? Very simple. Actually, what happens in the non-monic case is that you cannot apply division algorithm for non-monic polynomials directly. For division algorithm for integers is not always valid for non-monic polynomials. So what do you do? In that case, apply division algorithm over rational numbers. Apply division algorithm for rational numbers to get a quotient e and a remainder h which are unique and have rational coefficients such that p of x equal to q of x times g of x plus h of x for all x, and either h is identically 0 or its degree lies in 0 to degree of q minus 1. That is the division algorithm for rational polynomials. This can be applied even when q is non-monic. So from here, what you have to do is, by trying out a few special cases, make an observation about the denominators in the coefficients of g. And try to remove those denominators somehow. You want integer polynomials, not rational ones. He has rational coefficients, so you want to remove the denominator somehow. So what you have to do is you have to multiply by a large integer so that the denominator gets removed, and then you arrive at a statement which is similar to the statement that you got for integer polynomials, and then you follow the entire proof that you did for integer polynomials and arrive at a contradiction. So that's how you have to approach the non-monic case. So this is an application of the idea of limits of a polynomial, and the idea has many uses later on also. So I won't be taking any more classes now, I think, and the remaining additional topics I will send you the PPT for that. And so you will find some more applications of the ideas we discussed in the additional topics also. So you might want to skip them now, or is there a shorter method to solve this question? No, maybe there is, but right now I don't have one in mind. In fact, okay, one short method is using calculus only. Instead of arguing using limits directly, I mean, instead of arguing using the positive and negative and all that directly, you can apply limits and use some things about integer sequences and all that. So using calculus, you can do. So, but that is exactly the same as this method. That method is just the, what to say, advanced machinery, and this one is just decoding that advanced machinery. So that method is pretty short, I would say. Using calculus also, it is pretty short. So if you find any other elementary method, discuss it on WhatsApp. I would like to see. So that's how it is. I don't know any other short method now. So what I was saying was, you will find many applications of the ideas discussed here in the additional topics. The additional topics, the question the topics that I have discussed, those are useful later on in later stages of competition and all that. But now, if you want to skip, you can skip them. They are a little bit more difficult than what I have discussed now. So that is the end of the polynomials lecture, and thanks everyone.
Thank you, Dada.